All right, today we're going to dive into a breakthrough that could finally get humanoid robots out of the lab and into our world. It's a brand new framework called the Behavior Foundation Model, and it's all about teaching robots not just to do things, but to actually learn and adapt on a completely different level.
So, you've all seen the videos, right? I mean, robots doing backflips, sprinting, carrying heavy boxes. It's incredible stuff. But have you ever stopped and wondered why that same robot that can do a perfect backflip can't also, pick up a VR controller and follow your lead? Why are they all so specialized? Well, that's the big question we're tackling today.
And this really gets to the heart of the problem. On one side, you have the specialist. Think of it like a world-class sprinter. They are unbelievably good at that one thing, running really fast. But you wouldn't ask them to compete in weightlifting, right? The dream, the goal, is the general purpose robot, an all-around athlete that can handle pretty much anything we throw at it in our messy, unpredictable world. Now, let's be super clear here. This isn't a hardware problem. The robots are amazing. This is a software and a training problem. Right now, teaching a robot a new skill is like writing a totally new piece of software from scratch every single time. A policy that's trained for walking only gets velocity commands. It has no idea what a VR signal even is. And that task-specific approach is the huge bottleneck holding everything back. But what if we could totally flip that on its head? What if, instead of teaching robots these isolated individual tasks, we could teach them a deep foundational understanding of behavior itself? Well, that's the core idea behind the Behavior Foundation Model, or BFM, and it is a complete shift in how to think about this problem. This quote from the research paper just nails it. It perfectly captures what's going on here. This isn't just a small upgrade. It's a whole new way of doing things. The goal is to stop building a library of separate skills and start building one unified understanding of movement that can be applied to any task. So, what do we really mean when we say behavior? In the BFM world, it's this powerful unified concept. The model learns to see all these different commands, whether it's walk forward at this speed, a complex signal from a VR controller, or a full body motion it needs to mimic, as just different dialects of the same language, the language of behavior. This lets one single policy do it all. So how in the world do you actually build a model this powerful? I mean, you can't just throw a bunch of random data at it and hope for the best. The BFM uses this really clever two-stage training process that's all about bridging the gap between a perfect computer simulation and our messy physical reality. And this right here highlights the core challenge. See, in a simulation, an AI basically has superpowers. It can know everything, the exact position of every joint, the perfect friction of the floor. It has privileged information. But a real robot, in the real world, it's limited to what its own sensors can observe. The absolute genius of the BFM is how it uses that perfect simulation to train a robot that can work with real-world limitations. Think of it like a master and an apprentice. In step one, you've got the master, an expert tutor who gets to train inside that perfect simulation with all the privileged data. It learns a massive library of behaviors. Then, in step two, the BFM becomes the apprentice. It learns by watching the master, but here's the catch. It's forced to learn using only the limited sensor data a real robot would have. This process, called online distillation, is how you transfer all that expert knowledge into a model that can actually work in the real world. Now, a few key techniques make this all possible. They use domain randomization, which is basically just making the simulation super unpredictable, changing the physics, literally pushing the robot around to make it tough and robust. Hard negative mining is like a coach forcing you to practice your weakest moves over and over. And at the very core is a special kind of architecture that doesn't just copy motions, it learns the fundamental patterns behind them.
Okay, the theory is fantastic, but does it actually work? The researchers put the BFM to the ultimate test on a real Unitree G1 humanoid robot, and they pitted it against some of the best models out there. Let's see what happened. So here's the lineup for the big showdown. You've got Hover, another generalist model. You've got the specialists, GMT and Omni H2O, each one a champion in its own very specific skill. Then they have a version of BFM trained the old-fashioned way, just to prove that their new two-stage method is what really makes the difference. And finally, you have the expert tutor from the simulation, kind of like the theoretical gold standard. And the results are, well, they're kind of staggering. Against the other generalist model, BFM doesn't just win, it significantly outperforms it across the board. But here's the part that really blew my mind. When you put it up against the specialists, BFM, the jack of all trades, isn't just competitive, it's often better than the models that were designed to do only one of these things. That's crazy.
Let that sink in for a second. The behavior foundation model delivers on its promise, big time. It achieves a level of versatility that crushes other general-purpose models, while at the same time performing at the level of a hyper-specialized expert. This is a huge, huge deal. But the story doesn't end there, because BFM learns the deep structure of behavior, not just individual tasks. It unlocks some truly incredible new abilities. Let's just call them its hidden superpowers. Superpower number 1 is behavior composition. Because the model understands the fundamental patterns of movement, it can actually mix and match them. It can take the essence of one behavior, combine it with the essence of another, and generate a totally new motion it has never, ever been explicitly taught before. So here's a simple example of how that works. The model has an internal code for walk forward, right? And it has another one for sidestep. By simply blending those two codes together, kind of like mixing two colors of paint, it can generate a brand new, perfectly smooth diagonal walk on the fly. It's almost like a form of robotic creativity. The second superpower is just as game-changing: incredibly fast learning. Usually, teaching a robot a new skill means starting over, which is super slow and inefficient. But with BFM, you can just freeze all its existing knowledge, all that foundational learning, and just train a tiny new layer on top. The model only has to learn the small difference, the delta, between the new skill and what it already knows. And get this for an example, a side salto, a side flip. This is a really difficult move that the base model couldn't do. But instead of a massive, long retraining session, they taught it using this residual method. The model just leveraged everything it already knew about balance and movement and learned this complex new skill incredibly quickly. So, what does this all add up to? Let's take a step back and really look at the big picture here and what this could mean for the future of robotics. At the end of the day, the behavior foundation model isn't just another incremental improvement. It's a proof of concept. It's a validated framework that shows us a clear path forward, a way to finally build robots that aren't just one-trick ponies, but are adaptable, versatile learners that could actually operate in the chaos of our world. And that leaves us with this fascinating, almost dizzying final thought. For so long, the biggest problem has been how to teach robots anything complex. But with a foundation like this, that whole problem starts to shift. The question is no longer, can they learn? But what on earth should we teach them first? And that is an extraordinary new frontier to think about. Thanks for joining us.